Good morning, everyone. Thank you for joining us today. I'm Charan Gajjala Chenchu, a computer science graduate from the University of Houston. This work is done in collaboration with Dr. Kinam, Dr. Zayauddin, and Dr. Gavlu from the Department of Construction Management. We explore how combining muscle signals and video data can advance motion intention recognition for safer and more human-robot collaboration in construction. Let's begin now. Here's the outline of our presentation with introduction, experiment results, and conclusion at the end. Okay, coming to the introduction, as we all know, construction is one of the most labor intensive industries, often affected by accidents and delays due to unpredictable environments. Human robot collaboration, or HRC, offers a promising solution by enabling direct cooperation between humans and construction robots in shared workspaces. Unlike traditional automation, where robots work independently, HRC combines human flexibility with robotic precision. Right? It improves safety, boosts productivity, and addresses labor shortages by assigning hazardous and repetitive tasks to robots. With the support of AI, HRC systems can adapt to dynamic conditions, allowing for real-time decision making, faster project completion, and reduced material waste. However, construction robots still face major challenges in understanding human behavior and responding in real time. Accurate recognition of human recognition intention is critical for robots to stay in sync with workers and avoid collisions. This makes motion intention recognition a key enabler for successful HRC in construction. Our review shows that sEMG signals and video recordings are the two main modalities used for motion intention and action recognition. CNN-LSTM models are effective for sEMG, while transformers excel in video-based spatio-temporal analysis. Each has limitations, right? sEMG is affected by factors like electrode placement and subject variability, while video systems face occlusions, lighting issues, and high processing demands. Although both are well studied separately, direct comparisons are rare in the existing research, likely due to the lack of datasets combining both modalities under similar conditions. These research gaps gave us a purpose to develop a motion intention recognition system using two modalities, as we have discussed previously. And our key objective is to compare these two approaches under identical experimental conditions, which allows us to assess their relative effectiveness in terms of latency, accuracy, etc., and the suitability for HRC in construction settings. So the proposed methodology uh, the workflow as displayed in figures starts with data acquisition of raw signals and videos, which are then pre-processed into sequences as inputs to the models. The models are trained on these sequences for motion detection. Finally, the training curves and the metrics are compared and interpreted. In, in terms of the data acquisition and cleaning process, we collected data from three subjects performing four drywall installation tasks using two modalities, SEMG signals and video recordings. The SEMG data was captured from four muscles on the dominant hand of the subject, with each TXT file representing one subject performing one activity. Videos were recorded using a mobile phone, with each file corresponding to a single task instance. Each activity was divided into two phases, our groups, we can say intention consisting in the first 1 second and actual resulting in 8 classification labels. Both signal and video data were segmented using sliding window approach. To expand the video data set, augmentation techniques such as noise addition, brightness, and contrast adjustment, flipping were applied, tripling the number of samples. To address class imbalance in the EMG data, intention sequences were oversampled alone. Finally, EMG data was standardized and the video frames were resized and normalized for model input. This is a proposed hybrid CNN-LSTM architecture for training on signal sequences. This model is trained from scratch. The initial CNN blocks extract spatial features from the signals, and the following LSTM layers capture long-range temporal dependencies from these time series sequences. The output dense layer with softmax activation at the end computes the probabilities for classification. The intermediate dropout layer and the L2 layers mitigate overfitting. For video sequences, we used a pre-trained video SwinTransformer base model, which extends the image-based SwinTransformer model to capture spatio-temporal features in videos. We applied transfer learning by freezing all pre-trained weights initially, then unfreezing the final MSA module, layer normalization, and dense layers in stage 4 for fine-tuning. The MLP layer remained frozen to preserve high-level nonlinear features from pre-training, reducing complexity and overfitting. Finally, we added a custom classification head with a dense layer of 8 output neurons corresponding to the 8 target classes. Let's move on to the conducted experiment now. In the experiment, three subjects performed four drywall installation activities, as we can see lifting, carrying, holding, and mounting drywall activities. On the right side image, the plotted sample EMG signals can be seen in the left image. The signals are collected using open signal software via Bluetooth at a frequency of 500 samples or data points per second, while the videos were recorded simultaneously at 60 frames per second. This frequency difference is the reason for huge difference in data point count as well. We can see from the table. To balance this, video files were increased two times using image augmentations as discussed in the previous slides. In pre-processing, the first second of each files, txt and mp4, was labeled as intention group and the rest labeled as actual. Both of the modalities were segmented using a sliding window with 100 data points for EMG and 32 frames for sequence for the video data, with a 50% overlap to enhance variability and capture phase transitions. To address class imbalance caused by the short intention phases, EMG intention sequences were overlapped three times while the video data remained unchanged due to the prior augmentation. The EMG data was split into 70, 15, and 15% for training validation testing, and the video data set was split into 67, 17, and 17%, all of them maintaining balanced activity and subject distribution. Finally, video frames were resized to 224 cross 224 for model output. We trained CNN-LSTM model on EMG data and partially fine-tuned the pre-trained video spin B on video sequences, a separate validation test for use for model selection and performance evaluation. For both models, we used sparse categorical cross-entropy for integer encoded labels, Adam optimizer with a fixed learning rate for faster convergence, and class weights to address some imbalance caused by the misclassification of minority classes. To improve performance, we performed a git search over different configurations of L2 and dropout values, both varied in 0.05 increments. Coming to the training results, we have a training and loss accuracies for both training and validation sets. The video-based model showed consistently high performance with accuracy curves stabilizing over 90%, indicating strong generalization and minimal fluctuation. In contrast, the CNN-LSTM model reached around 85% accuracy with greater variability in validation and slower and more gradual loss decline. This suggests a complex learning process for the sEMG data. But however, more models trained without signs of overfitting. As we can see, the gap between the both curves, the training and validation is very close, right? The video swing model achieved higher accuracy across most activity classes and effectively recognized motion intentions with near perfect performance. In contrast, the CNN-LSTM model showed more variability with lower accuracy and especially for intention classes like carrying and mounting. Overall, the video-based approach outperformed compared to the sEMG-based model in stability, accuracy, and intention detection. The video-based model achieved 94% accuracy, outperforming the CNLSTM model, which reached only 80 to 86.8% over. So in terms of speed, the LSTM model was faster, taking 40 milliseconds per prediction on average compared to 150 seconds for the video SwinB model. So we can say that for time-sensitive tasks like safety monitoring or real-time lifting, signals offer advantages due to their resilience to lightning and occlusions as well as portability in dynamic environments. On the other hand, video models benefit from rich contextual awareness, making them suitable for multi-purpose coordination, collaboration activities, and adaptive planning. With compact cameras now mountable on mobile robots, portability issues are also being addressed. As shown in the graph, the optimal approach depends on the use case, right? A fusion model or quantized model could combine the speed of the EMG and with the depth of the video and the accuracy, offering a balanced solution for real-world construction applications. In conclusion, HRC has the potential to greatly enhance productivity, safety, and quality in construction industry. While our goal wasn't to declare a winner, both models performed well without overfitting, despite class imbalances and subject variabilities. Each model offers distinct advantages. For future work, we can have quantization, synthetic data, and simulations to mitigate data scarcity. We can also use fusion architectures that combine the strengths of the both EMG and video for more robust performance in dynamic environments. We can also use robot control interfaces along with these models to allow and prototype and check the real actual capability in terms of practical applications. So that's the end of our presentation. Thank you all for your attention. We are happy to address any questions you may have. Thank you.